That's what I want to go to.
All right. So yesterday we finished talking about differential approximation. So today, what we're going to do is start talking about the rules of differentiation, right? That is to say, we already discussed how differentiation can be expanded, generalized to the case of a vector valued function, right? We just take the derivative of each of the components. And we recorded a bunch of properties that carried over from calculus 1 into this setting, yeah? Now we want to do the same thing for multivariable functions, okay? Okay, so here's the theorem. We'll take f and g real value functions of n variables with the same subset of Rn as their domain. That is to say, f and g have the same domain. Okay, then what will we say? Firstly, where the gradient of f and the gradient of g exist, we have that the gradient of a times f plus b times g exists, and we have a formula for it. A times the gradient of f plus b times the gradient of g. Whereas you might have presumed by this point, a and b are scalars or real numbers. Okay, remember, it's often very useful to think of the gradient as the derivative, right? That is to say, remember in calculus 1, we said that the derivative is linear, right? We can split the derivative across the sum and pull out the constants. This is saying the same thing for the operation of taking the gradient, right? Again, the gradient behaves much like the derivative for a multivariable function. Okay. Right. So if I was interested in finding the gradient of the product of these two scalar functions, what do you guess is a way I could do that? Yeah, we'll take a product rule of some kind, right? In particular, it's just what you would expect carrying this analogy of treating the gradient like a derivative, right? You have the one of the functions times the gradient or derivative of the other, plus the second function times the gradient of the first. Really quick here, just some dimensional analysis. Remember, we're assuming that f and g are scalar functions, right? When we take the gradient of a scalar function of n variables, we get out a vector valued function that has n components, right? So the left-hand side is the gradient of the product of two scalar value functions, which in turn is a scalar value function. We get a n component function of n variables. And on the left-hand side, we have a scalar times a vector value function. A scalar function times a vector value function. We add them together, we get a vector value function, right? Just making sure that all the dimensions work out here. Anytime we write an equation with vectors and scalars, especially when those things are variable or described by functions, it's usually worthwhile to just take a second and make sure that you wrote a statement that type checks, right? That at least the dimensions of the things on both sides of the equation are the same. Yeah? Yes.
So when we look, we see like gradient FG. Like the main thing that we think about is like F times gradient of G plus G times the gradient of F, not like the gradient of F times G.
I just wrote it this way because usually we put scalars in front of vectors. As long as you keep yourself straight on what you're doing, I don't mind the notation, whatever you use. But this is a surefire way to remember that now you're scaling this function gradient of G by the scalar function F. But if you write it a different way and still compute it correctly, that's fine with me. Okay. All right. So additionally, we can state some form of the quotient rule. The gradient of F divided by G is equal to scalar function G times the gradient of F minus scalar function F times the gradient of G all over G squared, where of course this formula only applies where G is not equal to 0, right? Okay. Fourth, we have a modified version of the power rule. Okay, so let's let alpha be any real number. And suppose f raised to the alpha minus 1 exists. That is, I'm multiplying the scalar function alpha minus 1 times together with itself, right? A loose interpretation here. Then the gradient of the function f raised to the alpha power must exist. And the gradient of f raised to the alpha is equal to alpha times f raised to the alpha minus 1 times the gradient of f. Right, so you take the power down and subtract 1, just like the product rule. And there's a bit of a chain rule feel to this too, right? We're tacking on, multiplying the gradient of f, the inside function. Okay, so the power rule, and you might interpret this as a weak form of the chain rule. But let's do a quick example about this, and then we'll talk about chain rule in general. I omit it from this list because it takes a little bit of work to correctly interpret the chain rule. We'll talk about that in a second. But first, an example. Okay, so let's suppose H evaluated at the vector 3, 7, 1 is equal to 4. And the gradient of H evaluated at that same vector, 3, 7, 1, is equal to the vector negative 8, 0, 4. Let me ask you to calculate gradient of square root of H at this point. 3, 7, 1. What are we going to use to do this? Last property, right? We modify chain. Yeah. Do you have a question?
No.
You were going to say that. Is there a perspective? Yeah. Yeah, good. Good. Okay. So let's use property 4. With alpha equal to 1/2. Well, then you can write the gradient of root H is equal to, we bring the power down and we take alpha minus 1. So 1/2 minus 1 is negative 1/2 times the gradient of H. Or if you like, this is 1/2 times root H times the gradient of H. So then if we want to evaluate the gradient of root H at the point 3, 7, 1, we'll just plug in the point 3, 7, 1 everywhere we have an H. Right? So that is to say, we got 1 divided by 2, square root of H evaluated at 3, 7, 1, times the gradient of H evaluated at 3, 7, 1, which handily we were just given in the problem, right? So we get 1/2 times root of H at 3, 7, 1. We were told that was 4, right? So 4 times the vector gradient of H evaluated at 3, 7, 1, which is negative 8, 0, 4. Or in other words, what did we get here? Negative 2, 0, 1. Really, the point of this exercise is, how do I evaluate this at a point? I just plug it into every place the function H appears, right? All right, so let's start to talk about the chain rule, which is, can anybody tell me what the problem is? Why the chain rule becomes more complicated in the multivariable setting? Yeah. Mhm. Yeah, right. So the chain rule has to do with composition. So you have an inner function and an outer function. And if our outer function is a multivariable function with real values, a scalar function, then we go from Rn or some subset of Rn into R. The inner function, the function we're composing with, can have anything as its domain, Rm for some integer different than n, even, right? The inner function is a function from Rm to Rn in general. And in order to apply the chain rule in a naive generalization, we have to say what the derivative is of a function of m variables that has n-dimensional vector output, which is not something we've done yet, right? We've only described what the derivative is of a vector value function of a single variable. And now what we have done in the past couple days is describe what the partial derivatives are of a multivariable function that has a real output. And I've kind of emphasized this analogy that the gradient behaves something like a derivative. But we don't know in general what the definition of the derivative is of a function from Rm to Rn. And in fact, we're not going to say the full definition because it requires some familiarity with linear algebra and the use of matrices. So if you'd like to read about it, it's in the appendix to chapter 2, the more linear algebra section. You know, at the end of every section, there's a little piece about linear algebra. So those of you with experience might want to look at that, and I'm happy to talk about it, but we're not going to talk about it in class since linear algebra is not a prerequisite. So what we'll have to do is make some ad hoc definition of what the derivative of an inner function can be. Okay, so here's the setup for the chain rule. We're considering the following situation. We want to go from Rm into Rn into R. Here's some function f. These are our main objects of study for the moment. Functions of n variables that output a real number. And we'll look at some function x hat going from Rm to Rn as the inner function. Okay, and let's just draw what's going on here for an arbitrary vector in Rm. We'll take t hat, t1 up through tm. This gets sent to x hat of t hat, which is equal to x1 t1 up through tm, comma, all the way up to xn evaluated at t1 through tm. Right, as a function from Rm to Rn, x hat has n component functions, each of which depend on m variables, t1 through tm. Right, and then we'll take this and map to just a scalar f of x hat of t hat. Okay, so we want a situation like in Calc 1. We take two functions f and g that go from R to R, then the derivative of f composed with g is equal to f prime of g of x times g prime of x, right? This is what we want to imitate in the setup here. That is to say, so something like f of x hat of t hat prime is equal to f hat, I'm sorry, f prime of x hat t hat times x hat prime of t hat. Okay, so there's a couple obstructions to making sense of this formula. First of all, what do I mean by the derivative of f? What I wrote makes no sense, right? Or at least it's ambiguous. This is an analogical statement, yeah. This should be the gradient of f, yeah. Or more correctly, what we're looking for is the gradient of f x hat of t hat. Okay, now making that logical maneuver, this is a vector.
I have a question on the words alpha and f dot g.
F comma g, that is both these functions go from R to R.
Underneath it.
Oh, this is composed with, yeah, f of g of x, f of g prime of x. Yeah, this open circle means composition. Okay. All right, so this is a vector now. I have to modify what I mean when I say times here, right? What should I replace this multiplication with? Yeah, a dot product. Yeah, take a dot product of some vector. I'm not sure of it. This is where we have to make the ad hoc definition of what the derivative of x means, a function from Rm to Rn. Yeah. Okay, so with all that being said, let me tell you again. Let's suppose, just as my previous ramblings, that t is equal to t1 up through tm, and x hat of t hat is again just as we said x1 of t hat up to xn of t hat, and f of x hat t hat, a real value function. Okay. Well, it's a function of x hat, but it's also a function of t hat, right? Okay. So then furthermore, let's let a hat be some specific element of Rm. And define the partial derivative of x hat with respect to ti as equal to the vector of the partial derivative of the n components of x hat with respect to ti. this is the right notion. This is what we want to define to make this chain rule concept rigorous. This is the some vector that we had not previously defined, right? Up till now, we had only defined partial derivatives for multivariable scalar value functions. This is an ad hoc definition I'm making for the partial derivative of a vector value multivariable function. Okay. So just for those of you who know some linear algebra, the thing that we actually call the derivative of x hat is a matrix of all these partial derivatives of each component or each of the i's. If you haven't taken linear algebra, don't worry about that. This is the only thing we need to think about right now. Okay. Okay. So we'll define this partial derivative of x hat with respect to ti. And we will suppose it exists at a hat and f is differentiable. At x hat evaluated at a hat. Okay, this is all analogous to what you have to assume when you state the chain rule in the single variable case, right? You have to say, well, the outer function has to be differentiable at the value of the inner function at the point you're evaluating, right? Same thing here. Okay. Then what we can say is the partial derivative of f with respect to ti, right? That is any one of these components of t hat, the variable that inputs to x hat, exists at a. And here is what we can say. The partial derivative of f with respect to ti evaluated at a hat is equal to, just as we guessed before, the gradient of f of x hat evaluated at a hat dot the partial derivative of x hat with respect to ti evaluated at a hat. Yes. I is just I goes from 1 to m. I'm just saying for each of the components of the input variables of the function x hat. Yeah, good. Thank you for pointing that out. Okay, so this was a lot of definitional work, but we really do want a version of the chain rule that applies to multivariable functions. So, and this is a pretty nice formula, right? We know how to compute dot products. The only thing kind of unusual about it is this definition we have to make. Okay, now let me show you a good way to remember this formula. Also written as partial f partial ti is equal to, if I actually just take this dot product and write it out in long form, the first component of the gradient of f is partial f partial x1. Remember, because f is a function of x, right? So I can differentiate with respect to each of the x terms times the partial derivative of x1 with respect to ti plus partial f partial x2 times partial x2 partial ti, all the way up to partial f partial xn times partial xn partial ti I. So I think this is kind of an easier form to remember, right? Because it looks like cancellation is happening here, right? If these were actually fractions, which they're not, partial x1 cancels partial x1 here, and you get partial f, partial ti. You're getting the contribution from each of the component functions of x, x1, x2, x3, up to xn, of the rate of change with respect to ti for every I. Okay, so I feel like this is the easy formula to remember instead of remembering what the definition is of the partial derivative of x hat. I mean, it's not that hard, but I feel like this is the easiest thing. Right, and then you have this mnemonic thing that is like cancellation. It's not actually cancellation because these aren't fractions, but the way it looks helps me remember that at least. Maybe it can help you too. Okay, so let me just say, it seems like some form of cancellation. I'll underline seems because it's not actually, but that may help you remember the formula. Okay, so let's do a couple examples to actually apply this. So let's let g of xy equal x times y. And let's also suppose that x is equal to u minus v and y is equal to u plus v. And so x and y are each in their own right functions of two variables. Okay. Let me ask you to calculate partial g, partial u, and partial g, partial v. Okay. So if we want to apply the theorem straight up, let me first ask you, what is t hat here and what is x hat? Remember our little diagram here. Yeah, it's the thing all the way on the left. It's the first input. Yeah.
X or Y.
Okay. No, because our outside function is g, meaning our inside functions are x and y, meaning they're in the middle. U and v are the inputs to the inputs of g. Right? So t, the vector t, note from the theorem, the vector t will just be u comma v. Right? And the vector x hat will be x of u comma v, comma y of u comma v. Using the notation of the theorem. Okay. So, what should we do first in order to calculate these two partial derivatives? Well, what would you like to do first? There's a few things we need to do. Doesn't really matter what order we do them in. So it's really just personal preference. Does anybody have one? Okay, if nobody has one, that's fine. Let's do the thing we're most familiar with first. Let's calculate the gradient of G. Okay. So the gradient of G is equal to the vector of partial derivatives. What's the partial derivative of G with respect to X? Yeah, it's just Y. And what's the partial derivative of G with respect to Y? Yeah, just X. Good. That was easy. Now, let's take the partial derivative of X hat, right? With respect to, we have to do both U and then V, right? Since we have to do it with respect to each of the components of T. The components of T are U and V. So just going by the definition I gave you here. Well, let me ask you, what's X1, the first component of X hat? Yeah, it's just the formula for X, right? So this is, I'll write this out in long form. X U comma V, comma, the partial derivative with respect to U of Y of U comma V. Or in other words, the partial derivative with respect to U of our formula for X in terms of U and V. What's the partial derivative with respect to U here of X? Yeah. Well, remember V is a constant with regard to U. So it's just one, right? We got one from the U summit. Okay. U, I'm sorry, one. And the partial derivative with respect to U of Y is also just one, right? Okay, good. So now we'll take the partial derivative of X hat with respect to V, which is the partial derivative with respect to V of X U comma V, comma, the partial derivative with respect to V of Y U comma V. Okay, what's the partial derivative with respect to V of X? Okay, so we get a 0 from the U, and what do we get from negative V? -1, good. And the partial derivative of Y with respect to V is just 1. Okay. But now we have all the information we need to compute these two partial derivatives. Partial derivative of G with respect to U is equal to the dot product of the gradient of G with the partial derivative of X hat with respect to U, which was just 1 comma 1. So what do we get here? We get Y plus X. Okay, so this is a correct answer, but things might be a little more transparent since I was differentiating with respect to U. It's kind of nice if it's easy for me to just plug in the formula I had for x and y in terms of u and v, right? Since I was differentiating with respect to u, I might like to see a u or v in the final answer. Okay, so what do we get? Plus v plus u minus v, or in other words, 2u. Okay, and let's take the partial derivative of g with respect to v, the gradient dotted with the partial derivative of x hat with respect to v, which we computed as -1, 1. So we get negative y plus x, or negative u plus v plus u minus v, which is equal to negative 2v. Okay, great, we got an answer. We executed the theorem. How do we know we're right? How do we know that this is actually the partial derivative of the composition? Yeah. You should get the same thing. Let's do that just to be sure we're not crazy. So g of u comma v is equal to the expression for x in terms of u and v times the expression for y in terms of u and v, which according to algebra is u squared minus v squared. What's the partial derivative of this with respect to u? 2u. And the partial derivative of this with respect to v? Negative 2v. Okay, so we executed the chain rule correctly. Why didn't I just do this to begin with? I don't have to manufacture a bunch of vectors and take dot products. I can just plug in the formulae and differentiate directly. What's the point of the chain rule? Yeah. Yeah, well, so you can always plug in the expressions for the vector x hat. You can plug in the vector t hat and get a new expression. But most often that's a lot of algebra, right? This example was curated specifically so that we could check our work in an easy fashion. Most times, most compositions you can manufacture are like much worse than this, right? So on average, the chain rule saves you a lot of time as opposed to just plugging in the equations that you're composing. Okay. All right. So let's look at another example. I'm just going to write this down and then you guys work on it for a little bit and we'll see how it goes. So let's let f of xy be equal to x squared y plus xy cubed. And we'll also say that x is equal to 5s squared plus 7st. And that y is equal to 3st plus 4t squared. And I'll ask you to find partial f, partial s, and partial f partial t. So let's just take a couple minutes to work on this. Yeah.
Can you like make something kind of like a gradient?
Yeah, sure. So remember that f is also a function of s and t. So yeah, you could do the gradient with respect to s and t. Okay. So let's see what we come up with here. So how's it going? What are we thinking? Is it easier to substitute or use the chain rule? Anybody try substitution here? Yeah, it's a bother. Let's talk about this. So what's our first step? How do we proceed? Yeah. Yeah, sure. I wrote this like I don't expect you to have to write this every time, but that is good. That's a good thought process, right? You want to identify what's being composed with what. So yeah, where t hat here is s comma t, right? So that's why it's kind of confusing because like we might rename the variables a bunch, and x hat will be x and y again. Okay, good. So then what do we compute? Sure, let's calculate the gradient of f. What do we get for the gradient of f? 2xy plus y cubed. That looks good to me for a partial derivative with respect to x. And how about somebody else tell me the partial derivative with respect to y here? Plus 3x y squared. Good. All right. Now what should we do? Yeah, sure. So partial x hat with respect to s will be again the partial derivative of sorry, with respect to x of S comma t on the partial derivative with respect to s function y of s comma t. Okay, so what does this give us? Partial derivative of x with respect to s. I don't know what to say. Okay, so we have 10s. Good. We bring the 2 down. We get 5 times 2 is times s plus 7. We differentiate differentiate this with respect to s. We get 7t, right? And for the second one, what do you think? So we're differentiating with respect to s here. Why? That's okay. Yeah, right. So this, I'm glad you said this, right? Because remember, when we take the partials with respect to the variable vector, we hold the variable we're partial differentiating to constant in all the components, right? So we stick with s. So the partial derivative of y with respect to s is 3t, and this goes to 0 because there's no s part of it. Okay, good. The partial derivative of x hat with respect to t. I'm not going to write this time. I think we're internalizing this slowly. Okay, what if I take the derivative of x with respect to t? What do I get? Should get just 7s, right? And the partial derivative of y with respect to t is 3s plus 8t. Okay. Now all that's left is to take some dot products. Partial derivative f respect to s is the gradient of f. Y plus y cubed x squared plus 3xy squared dot dx hat ds 10s plus 7t 3t, and partial derivative of s with respect to t, and we take gradient dotted with partial x hat partial t. 7s 3s plus. Okay. So in our last example, I went to the trouble of resubstituting and putting my final answers just in terms of u and v. That's not really important to me. That was just to illustrate that we could get the same answer by just substituting. As long as you carry any problem that involves the chain rule to this point, that's fine. You don't have to actually do the dot product. I think we all know how to compute a dot product at this point. And plugging in the expressions for x and y in terms of s and t is just a bunch of unnecessary algebra. That's not really the point of what we're trying to learn, right? So this is fine. So as long as you recognize the right steps and form the right vectors to take the dot product of. Okay. Good. All right. So now we're getting into some of the flavor of the fact that differentiability in the multivariable context is a bit more subtle. There's a lot first of all, there's a lot of different definitions of what a derivative is, right? We talked about partial derivatives. We talked about gradients. We made this impromptu definition of what the derivative of a vector valued multivariable function is, right? There's lots of, we have to make a new definition for each time we want to differentiate a new type of thing, right? So now we're going to talk about yet another type of derivative, namely the directional derivative. Okay, so I'll tell you the definition and then we'll talk about what this is supposed to mean. Okay, let's suppose f is differentiable. Function of n variables at p hat, an element of Rn. That u hat is a unit vector. What's a unit vector? Yeah, it's just a vector with magnitude 1. So remember that a vector is described by a direction and a magnitude. So sometimes we have the terminology that a unit vector is just referred to as a direction because we can ignore its magnitude. It's 1. For any multiplicative purposes, it doesn't matter. Right? Sometimes we call a unit vector a direction. Use that terminology here for a while. Then the directional derivative of f at p in direction u hat is given by capital D sub u f evaluated at p is equal to the limit as t approaches 0 from the right of f of p hat plus t times u hat minus f evaluated at p hat, all divided by t. Okay, so just looking at this, this is very similar to the definition of derivative in calculus 1. Yeah. Plus t times u hat, close parentheses. Yeah, right. So remember, this is just like the definition of the derivative in calculus 1, right? We have f at p with a little bit of variation minus the actual value of f at p divided by t. Yeah. Yeah, so no, it doesn't have a hat here. So our convention is that that means it's a real function. Right. We won't get back to talking about functions with multivariable functions with vector output until close to the end of the course. This is a much more complicated issue if you don't have linear algebra on hand. So we're only going to discuss a few special cases at the end of the course about those more complicated functions that go from Rm to Rn. Okay. Good. So just a couple quick comments here. Why do we approach 0 from the right? instead of taking it two-sided. Yeah. Yeah, exactly. Because we're looking in the direction of u, not negative u. We're going to look at only positive scalars. Good. Okay. So, yeah, just conceptually, hopefully this makes some kind of sense, right? Because we're looking at what happens at t gets smaller and smaller and smaller. So what we're trying to record is the rate of change when we move on the graph of f, right? It's like kind of like walking around on a mountain. And then we're pointed in the direction of u based at the point p. And we make that quantity, what we scale u by, smaller and smaller and smaller until we get a rate of change just at p, pointing in the direction of u. Okay. Okay, so let's record that. This represents the instantaneous rate of change of f at p, sorry, with respect to distance in Rn in the direction of u. Of u with speed 1. What do I mean by that? Where does that come from? What do I mean by speed 1? Yeah. Yeah, exactly. The unit vector, the rate at which it's moving. If we're talking about the rate of change of direction, there's like kind of a implicit movement analogy going on here, right? So the magnitude of the vector u is the speed that we're traveling at. And so since we insisted that u be a unit vector, we're considering speed 1. Okay. So this is the same old story for any definition of any derivative that we make. It really boils down to a limit. And in fact, that's true for integrals as well. But our goal, we don't want to compute limits every time we compute a derivative. Our goal is to come up with some efficient computational formula to calculate these directional derivatives. So let me tell you what that is. It's actually quite nice. Okay, so let's suppose f is differentiable at p. An element of Rn and u a unit vector. Then the directional derivative in direction u of f at p is simply equal to the gradient of f at p dotted with u. Okay, so the gradient, in some sense, captures all the differential information we want. We just want to know what component of the gradient of f at p points in the direction u. Okay, So what is the formula that involves the angle between vectors for a dot product? Anybody remember this? Yeah, where theta is. Yeah, good. What's the magnitude of u? Yeah. Okay, so we're out of time, but on Monday, we'll use this formula to deduce some facts about the directional derivative. All right, just some sign analysis we can do just from knowing this. Have a great weekend. And sometime tomorrow, I'll send out a practice exam. I know it's a little early, but can't hurt. Well, yeah, you too. I think we should be more careful before we say that.
I just like saw you about it.
Mhm.
So I was just visualize it.
Well, remember, by and large, we are at a loss to actually visualize anything.